Mathematics in the last 25 years. The concept of mathematics. Mathematics is one of the oldest things human beings have ever done. Long before writing, before cities, before science as we know it, people were already counting, measuring, and comparing. We counted animals, measured land, tracked time by the stars, and tried to understand patterns in nature. In that sense, mathematics began as something deeply practical, a survival tool. But very early in its history, mathematics took a turn that would define it forever. It became less useful. By the time of ancient Greece, mathematics had started to drift away from immediate application. When Euclid wrote Elements more than 2,000 years ago, he was not trying to solve engineering problems or improve agriculture. He was asking a different kind of question. If we assume a few simple truths, what must logically follow? This marked a profound shift. Mathematics became not only a tool for solving problems, but a discipline concerned with truth, necessity, and structure. It became a way of exploring what must be true, even if that truth had no obvious use. From that moment on, mathematics followed two paths at once. One path remained practical, arithmetic, geometry for construction, mathematics for astronomy, navigation, and later engineering and physics. The other path became increasingly abstract. Mathematicians began studying numbers not because they counted anything, but because they had interesting properties. They studied shapes that could never exist physically. They invented structures that lived only in the mind. And over time, something remarkable became clear. Most mathematics is not useful. In fact, the vast majority of known mathematics has no direct application at all. Entire fields are devoted to objects that will never be measured, built, or observed. Many mathematical results will never be used outside mathematics itself. This is not a secret, and it is not considered a problem within the field. It is simply how mathematics works. What makes this even more interesting is that mathematics has always known this. Mathematical research does not operate under the assumption that usefulness is a good guide to discovery. On the contrary, history has shown again and again that the most transformative applications of mathematics often come from ideas that were once considered completely useless. Number theory was once described as the purest and most impractical branch of mathematics. Today it secures the internet. Non-Euclidean geometry was once a logical curiosity. Today it is the language of general relativity. Linear algebra was once abstract manipulation of symbols. Today it underpins machine learning, computer graphics, and data science. Because of this long history, mathematics has developed a unique research culture. Mathematicians do not ask first, what is this good for? They ask questions like, is this idea consistent? Does it reveal a deeper structure? Does it unify many problems into one? Does it open a new way of thinking? Mathematics accepts that most ideas will never leave the discipline, and that a small number will change the world, often centuries later, and often in ways no one could have predicted. In this sense, mathematics is not a factory producing solutions on demand. It is more like a vast intellectual reservoir. Most of it is never used. But when humanity needs something new, a new way to communicate, to compute, to see, or to understand, mathematics is already there, waiting. With that perspective in mind, I would like to take you on a journey through the last 25 years of mathematics, not as a technical survey, not as a list of equations, but as a story of ideas, ideas that were abstract, strange, and often seemingly irrelevant, and how some of them quietly became essential to modern life. We will talk about shapes and spaces that changed physics, numbers that transformed cryptography, abstract geometry that made medical imaging faster, and mathematical structures that now shape data, artificial intelligence, and our understanding of the universe. And throughout, I want to emphasize one key point. Mathematics does not advance by chasing usefulness. It advances by expanding what can be understood. With that in mind, let us begin with one of the most profound achievements of modern mathematics, understanding the very nature of shape and space itself. Geometry and shape, understanding space itself. The Poincaré conjecture, what is a sphere really? One of the most famous breakthroughs happened in geometry. Imagine a rubber object, something you can stretch and bend, but not tear. A circle, a square, and a triangle are different shapes, but a coffee mug and a donut? They are the same shape, topologically. Each has one hole. Imagine a rubber object, something you can stretch and bend, but not tear. A circle, a square, and a triangle are different shapes, but a coffee mug and a donut? They are the same shape topologically. Each has one hole. When mathematicians say that an object is a sphere, they do not mean that it looks round. They mean something much more abstract. In topology, we are allowed to stretch and bend shapes, but not tear them. What matters is not appearance, but whether the shape contains holes. Henri Poincaré asked a profound question. If a three-dimensional space contains no hidden holes at all, if every loop inside it can be shrunk to a point, must that space at its deepest level be a three-dimensional sphere? The answer turned out to be yes, but proving it required nearly a century and completely new mathematics. Why does this matter? Because understanding the shape of space is fundamental in physics, cosmology, and data analysis. It also introduced new mathematical tools that now appear in image processing, medical scans, and machine learning. Sphere packing. How tightly can you pack objects? Here's a simple question. How tightly can you pack oranges in a box? In 3D, the answer was known since the 1600s. But what about 8 dimensions or 24 dimensions? That sounds absurd. But high-dimensional spaces are exactly what we use in digital communication, error-correcting codes, and data storage. In 2016, Marina Wiazowska solved sphere packing in 8 dimensions. A week later, 24 dimensions followed. Why does this matter? Because sphere packing tells us how much information we can transmit, how many errors we can correct, and how efficient communication can be. This is mathematics that quietly powers satellite communication, mobile networks, and the internet. Number theory, the secret life of numbers. Prime numbers and patterns. Prime numbers, numbers divisible only by 1 and themselves, seem random. But are they? In 2004, mathematicians proved that primes contain arbitrarily long arithmetic sequences. For example, 5, 11, 17, 23, 29 are all prime and evenly spaced. What mathematicians proved is not that this particular pattern continues forever, but something far more surprising. No matter how long a pattern you ask for, 5 primes, 10 primes, or 1,000 primes in perfect arithmetic order, such a sequence exists somewhere among the primes. This was shocking. It showed that deep order exists inside apparent randomness. Prime gaps. How close can primes be? In 2013, something remarkable happened. For the first time in history, mathematicians proved that prime numbers do not drift apart forever. Yitangjang showed that there exists a fixed number n, a universal upper bound, such that infinitely many pairs of prime numbers differ by at most n. In Zhang's original proof, that number was very large, 70 million. This did not mean that prime numbers suddenly came in neat pairs 70 million apart. It meant something deeper. No matter how far out you go along the number line, you will always find prime numbers that stay within a fixed finite distance of each other. What followed was extraordinary. Within weeks, mathematicians around the world joined forces, many through open online collaborations. They refined Zhang's methods, sharpened the arguments, and introduced new ideas. Step by step, the bound was pushed down, from tens of millions to thousands, and then to hundreds. Today, the best proven result is n equals 246. This means we now know that there are infinitely many pairs of prime numbers whose distance is no more than 246. We still do not know which distances occur infinitely often. The famous twin prime conjecture, which would correspond to n equals 2, remains unproven. But the conceptual breakthrough is profound. Prime numbers are not just random points scattered into infinity. Hidden within them is an enduring structure, a guarantee that closeness never disappears entirely. This didn't just answer a theoretical question. It introduced new tools that now influence cryptography, randomness testing, and secure communications. Algebra and symmetry, the mathematics of structure. Classifying symmetry. Symmetry is everywhere. Crystals, molecules, physics laws, and even music. Mathematicians describe symmetry using a language called group theory. Some symmetries can be broken down into simpler ones, others cannot. These indivisible symmetries are called simple groups. They are the atoms of symmetry. After more than 50 years of work, mathematicians achieved something extraordinary. They proved that every finite simple symmetry belongs to a known list, and that no others exist. In other words, we now know all the basic building blocks from which every finite symmetry in nature can be constructed. Why is this important? Because symmetry underlies particle physics, chemistry, and encryption algorithms. It also showed that modern mathematics often requires hundreds of collaborators, not lone geniuses. Computer-verified proofs. In 2012, a major theorem was fully checked by a computer. This wasn't the computer discovering the proof, but verifying every logical step. Why does this matter? Because proofs are becoming extremely long, errors are increasingly subtle, and computers can help guarantee correctness. This has influenced software verification, hardware design, and cybersecurity. Data, statistics, and machine learning. Topological data analysis, seeing the shape of data. Imagine a cloud of data points in a high-dimensional space. Traditional statistics asks questions about averages, variances, and correlations. Topology asks something very different. What is the shape of this cloud? Does it form clusters? Are there loops? Are there holes? Empty regions surrounded by data? Over the last 25 years, the key breakthrough has been turning these qualitative ideas into a practical, computable toolkit. Researchers developed methods, often called persistent homology, that track how clusters, loops, and holes appear and disappear as you change the scale at which you connect nearby points. In other words, instead of deciding on one arbitrary distance threshold, TDA looks across many thresholds and identifies which geometric features are stable and which are likely just noise. Topological data analysis makes these questions precise. It allows us to detect global structures in data that are invisible to traditional methods, and crucially, to do so in a way that is robust to noise, missing measurements, and nonlinear relationships. What does this enable? It enables us to discover meaningful structure in modern, complex datasets where classical tools struggle. In cancer genomics, it can reveal hidden subgroups of patients whose disease looks similar statistically but differs in underlying structure, potentially improving prognosis and treatment choices. In brain data, it can uncover recurring loops and state transitions in neural activity. In artificial intelligence, it can help analyze the shape of learned representations inside neural networks, offering new ways to diagnose, compare, and sometimes explain model behavior. In short, this has turned abstract topology into a powerful tool for analyzing messy, high-dimensional data, helping us move from local statistics to a more global, structural understanding of information. Understanding AI mathematically. Machine learning systems have become astonishingly effective. They can recognize faces, translate languages, diagnose disease, and generate text, often at or above human level. Yet for a long time, there was an uncomfortable question at the heart of this success. Why does it work at all? From a classical mathematical perspective, modern machine learning should not work as well as it does. Many neural networks contain far more parameters than training examples. In traditional statistics, this is a recipe for disaster. A model with too much freedom is expected to simply memorize its training data rather than learn anything meaningful. This brings us to a fundamental concept: training data. Machine learning systems do not discover knowledge on their own. They learn patterns by being exposed to large collections of examples, images, texts, sounds, measurements. The quality, structure, and bias of this training data profoundly shape what a model can and cannot learn. If the data is limited, noisy, or biased, the model will inherit those limitations. One of the central risks is overfitting. Overfitting occurs when a model learns the training data too well. Instead of capturing general patterns, such as what makes a cat, it memorizes irrelevant details. In simple terms, the model becomes excellent at the past, but unreliable in the future. For many years, theory predicted that modern neural networks should overfit catastrophically. Yet in practice, they often do not. This apparent contradiction has become one of the most important mathematical puzzles of the last decade. Mathematicians and theorists have discovered that the way neural networks are trained plays a crucial role. Training is not random guessing, it is a structured optimization process. Methods such as gradient descent tend to guide models towards simple, stable solutions, even in enormous parameter spaces. In effect, the training process itself acts as an invisible regularizer, favoring solutions that generalize well, even when many worse solutions exist. Another key question is convergence. Training a neural network involves adjusting millions or billions of parameters step by step. There is no guarantee, in principle, that this process should converge to anything useful at all. Mathematical research has shown that under surprisingly broad conditions, training dynamics tend to move toward regions of the model space that are stable, predictable, and resistant to small perturbations. This helps explain why training often works reliably, even in systems too complex to fully analyze. Perhaps most importantly, mathematics is now clarifying what kinds of patterns machine learning models can truly learn. Neural networks are extremely good at detecting correlations, statistical regularities, and repeating structures. They are far less reliable at causal reasoning, abstract logic, or understanding meaning beyond patterns. This distinction matters. A model may appear intelligent while failing in subtle but critical ways when conditions change. These insights are reshaping how we think about artificial intelligence. Instead of treating machine learning as a mysterious black box, mathematics is building a foundation that explains when models can be trusted, when they are likely to fail, and how their behavior reflects the data they were trained on. This work is essential for the future of AI. Reliability depends on understanding generalization. Fairness depends on understanding data bias and learned patterns. Safety depends on understanding convergence, stability, and failure modes. In short, mathematics is not making AI more powerful. It is making it understandable. And without understanding, power alone is not enough. Applied mathematics that change the world. Compressed sensing, seeing more with less. Imagine taking a blurry photo and still reconstructing the full image. At first, this sounds impossible. If information is missing, how could it ever be recovered? Isn't lost data simply lost? For a long time, mathematics and engineering agreed on a simple rule. To reconstruct a signal perfectly, you must measure all of it. This idea was formalized in the mid-20th century by the Nyquist-Shannon sampling theorem, which says that you must sample a signal at a sufficiently high rate, or else information is permanently destroyed. Compressed sensing overturned this assumption. What mathematicians discovered in the early 2000s is not that information can appear out of nowhere, but that real-world signals contain far more structure than we realized. The key insight: most information is redundant. Take a photograph. Even a high-resolution image with millions of pixels is not arbitrary. Most pixels are similar to their neighbors, part of smooth surfaces, or lie on simple edges and textures. In other words, although an image has many pixels, it has few degrees of freedom. Mathematicians describe this by saying that images are sparse when expressed in the right language, for example as edges, wavelets, or frequencies. Most of the coefficients are zero or very small. Compressed sensing builds on this simple but powerful realization. If a signal is sparse, you do not need to measure everything. You only need enough information to recover the sparse structure. How can missing data be reconstructed? Here is the intuition without equations. Imagine you are trying to reconstruct a picture, but you are missing many pixels. There are infinitely many images that could match the few pixels you measured. So, how do you choose the right one? Compressed sensing adds a rule. Among all images that fit the measured data, choose the simplest one. Simple here means the one with the fewest edges, the fewest non-zero components, the least complexity. This turns reconstruction into a mathematical optimization problem. Find the simplest signal that is consistent with the measurements. Surprisingly, this rule is strong enough to uniquely recover the original image, even when most of the raw data was never collected. Why this works in the real world. The miracle is not that we invent new information. The miracle is that nature itself is structured. Medical images, sounds, videos, and sensor data are not random. They are governed by physical constraints, biological regularities, and geometric simplicity. Compressed sensing exploits this structure mathematically. It replaces the question, did we measure every point, with the question, did we measure enough to identify the underlying structure? What has this enabled in the last 25 years? This mathematical discovery has had immediate, concrete consequences. In medical imaging scanning, traditional methods require long measurement times. Compressed sensing showed that far fewer measurements are sufficient, images can be reconstructed accurately, scan times can be reduced dramatically. This means shorter scans, less discomfort for patients, and higher resolution images. Hospitals worldwide now use compressed sensing in clinical medical imaging, photography, and signal processing. Compressed sensing underlies faster cameras, efficient image compression, and reconstruction from incomplete or corrupted data. It allows devices to measure less, compute more. In astronomy, radar, and sensor networks, data may be expensive or slow to acquire, measurements may be noisy or incomplete. Compressed sensing allows scientists to reconstruct signals from partial observations, reduce energy and storage costs, and recover signals that would otherwise be unusable. What makes compressed sensing remarkable is not just its usefulness, it is the fact that the mathematics was developed before many applications were imagined. The key ideas came from pure fields like linear algebra and optimization, and it changed what we believed was fundamentally possible. It taught us that data is not just about quantity, it is about structure. Compressed sensing did not teach us how to create information from nothing. It taught us how to recognize how much information was already there, hidden in structure rather than measurements. Cryptography and the quantum future. For decades, digital security has relied on a simple mathematical idea. Some problems are easy to do, but extremely hard to undo. For example, it is easy to multiply two very large prime numbers, but if you are only given the result, factoring it back into those primes is believed to be extremely difficult. This asymmetry is the foundation of much of today's encryption. It protects websites and online banking, private messages, digital identities, and secure communication between governments and companies. Classical computers, the computers we use today, are simply too slow to break these systems in any reasonable time. But quantum computers change the rules. Quantum computers do not just run faster versions of ordinary algorithms, they use entirely different principles, superposition and quantum interference, to explore many possibilities at once. In the 1990s, mathematician Peter Shor discovered a quantum algorithm showing that a sufficiently powerful quantum computer could factor large numbers efficiently. This was a shock. It meant that if large-scale quantum computers become practical, many of today's encryption systems could, in principle, be broken, not because they were poorly designed, but because the mathematical assumptions they rely on would no longer hold. This does not mean that encryption suddenly fails. It means that the mathematics underneath it must change. How mathematics responded. Instead of trying to build faster classical computers, mathematicians asked a deeper question. Which mathematical problems remain hard? even for quantum computers. Over the last 25 years, this question has driven an entirely new field, post-quantum cryptography. One of the most important discoveries is that certain problems from high-dimensional geometry appear to resist both classical and quantum attacks. This led to lattice-based cryptography. A lattice is a regular grid of points extending through high-dimensional space. Not 2 or 3 dimensions, but hundreds or thousands. Some geometric problems on lattices are extraordinarily difficult. Finding the shortest vector, finding the closest point, or decoding noisy lattice information. Crucially, no efficient quantum algorithms are known for these problems, and decades of mathematical research suggest they are fundamentally hard. This shifts cryptography from number theory to geometry, from primes to shapes, from theory to global standards. What makes this story remarkable is how quickly abstract mathematics became practical. Over the last decade, cryptographers designed encryption schemes based on lattice problems, security researchers tested them against every known attack, and international organizations evaluated their long-term safety. Today, lattice-based cryptographic systems have been selected as international standards for future secure communication, specifically designed to remain safe in a quantum world. These systems are already being integrated into secure messaging, digital signatures, cloud storage, and long-term data protection. You may never use a quantum computer, but quantum computers may one day try to read your encrypted data, including data recorded today and stored for the future. Mathematics is what stands in between. Your digital privacy does not depend on secrecy or obscurity. It depends on deep, abstract mathematical structures discovered long before quantum computers existed. This is a perfect example of a recurring theme in mathematics. Ideas developed with no immediate application become essential precisely when the world changes. Mathematical physics, black holes, and reality. In 2022, mathematicians achieved something extraordinary. They proved that rotating black holes are stable. This may sound like an obscure technical detail, but in fact, it goes to the very heart of whether our understanding of the universe makes sense. Black holes come in many theoretical forms, but one type is especially important: rotating black holes. In the real universe, almost everything rotates. Stars rotate, planets rotate, galaxies rotate. When a massive rotating star collapses, the resulting black hole almost certainly rotates as well. These objects are described by a solution to Einstein's equations known as the Kerr black hole. Non-rotating black holes are idealized mathematical models. Rotating black holes are what nature actually produces. Stability does not mean that a black hole never changes. It means something much more precise. Imagine a rotating black hole that is slightly disturbed by matter falling in, by radiation, or by gravitational waves from a nearby cosmic event. The question is, what happens next? A stable black hole does this. The disturbance gradually fades, waves disperse outward, and the black hole settles back into a calm, predictable state. An unstable black hole would behave very differently. Small disturbances could grow instead of fading. Space-time could become wildly distorted. The equations describing gravity might break down entirely. If that were the case, much of modern astrophysics would rest on shaky ground. Why proving stability is so hard? Einstein's equations are among the most complex equations ever written. They are non-linear, meaning small effects can interact and amplify in unpredictable ways. Proving stability requires showing that all possible small disturbances behave well, not just for a short time, but forever. Mathematicians had to show that. Energy does not concentrate uncontrollably. Waves near the black hole eventually lose strength, and no hidden runaway effects exist. This demanded new mathematical tools, deep analysis of wave equations on curved space-time, precise control of energy flow, and estimates strong enough to hold for all time. The final proof, completed in 2022, spans over 2,000 pages and builds on decades of earlier work. It is one of the most technically demanding achievements in modern mathematics. Why this matters beyond black holes. This result answers a fundamental question that physics alone cannot fully resolve. Do our equations behave sensibly when pushed to their limits? The answer in this case is yes. It means that Einstein's theory of general relativity is mathematically consistent, rotating black holes are not pathological objects, and our models of black hole mergers and gravitational waves are built on solid ground. When observatories like LIGO detect gravitational waves from colliding black holes, the mathematical stability of these objects is what makes those interpretations reliable. This story reveals something profound about the role of mathematics in science. Physics proposes equations, experiments test them, but mathematics is what tells us whether those equations are internally consistent, dynamically stable, and capable of describing reality over time. Without mathematical proofs of stability, even the most elegant physical theories remain incomplete. In this sense, mathematics is not just a tool for calculation, it is a judge of coherence. And in the case of rotating black holes, it has delivered a reassuring verdict. Our picture of the universe holds together, even in its most extreme corners. Conclusion. What have we learned? What do the last 25 years of mathematics show us? Old problems can be solved, sometimes spectacularly. Pure ideas lead to practical revolutions. Mathematics is increasingly collaborative, interdisciplinary, and essential to modern life. Mathematics is not finished. It is not cold or distant. It is a living language, quietly shaping medicine, technology, security, and our understanding of reality. And perhaps most importantly, mathematics reminds us that deep understanding is possible, even in a complex and uncertain world. Thank you.